Okay. So let me introduce Geoffrey Ye Li briefly. He's a chair professor at the Imperial College London, UK. Before joining Imperial in 2020, he spent around 25 years with Georgia Tech and AT&T Labs in the USA. He has made fundamental contribution to OFDM, established resource cooperation framework for wireless networks, and pioneer the use of deep learning for communication. Professor Lee has authored over 700 journals and conference papers, holds more than 40 granted patents, and his work has received over 80,000 citations with an H index of 130. He has repeatedly been named a highly cited researcher by Web of Science and is the recipient of the 2024 IEEE Eric E. Sumner Award alongside numerous IEEE Society uh, distinctions, including 2019 IEEE ComSoc Edwin Howard Armstrong Achievement Award. Let's welcome Professor Geoffrey Ye Li.
Thank you for your introduction.
Well,
Good afternoon, everybody. I'm Geoffrey Ye, and today I'm going to give a talk on convergence of federated learning with communication distortions. This is a topic which combine communications and machine learning, and the work was contributed by my previous postdocs and visitors and PhD students. They are Professor Senlong Zhou, who was my postdoc several years ago, and right now he's a professor at Beijing Jiaotong University, and Professor Miss Yat-sen, who is a visiting PhD student in my group, and Professor Hao Yi, he was my PhD student at Georgia Tech, and Dr. Oya Wang, who is was my PhD student. Right now, he's a postdoc in my group. Well, this is the outline of my talk, and I will talk in general about the convergence of the federated learning in one with wireless communication distortions. I will divide my topic into three sections. The first section is we talk about centralized federated learning. Then I talk about decentralized federated learning, and afterwards I talk about extended federated learning framework, which introduced our recent publications in precondition in exact stochastic ADMM. Well, let's start with the this kind of the work talk. So federated learning. So nowadays many people talk about federated learning or whatever, machine learning for communications, and where we're trying to apply machine learning to improve wireless communication systems. For example, we can use a neural network to perform channel estimation or perform joint channel estimation and signal detection and so on. And we can also use machine learning or especially reinforcement learning for resource allocation and so on. So for all of these apply machine learning for communications, so we're trying to use those machine learning as a tool to improve the performance of communications. Then we are thinking about another way. How can communication can help AI or help machine learning, artificial intelligence in our future life? That's one of the interesting questions, because we are thinking about 6G. Everybody is talking about the 6G now, because For the 5G, we may use the machine learning to improve the performance. For 6G, because in the future, machine learning will be in every way of our daily life. So how can we design communication system to facilitate machine learning? That's an interesting question. And machine learning is one of the machine learning approach that can be used or applied in communications. More important, federated learning is enabled by communication. Let's just first introduce the basic concept of the federated learning. So the idea of the federated learning is to train a joint model but it's fine. To train a joint model, but the data is stored at different devices here. So for example, sorry about it. So here assume we are training a joint model and using the data which is stored at different devices. Of course, one of the direct idea is that we transfer those data directly to that the server or fusion center, and then we use a regular method, machine learning method to train that. However, that can cause a security issue, and also to communicate, send the huge data set to the fusion center or server may need lots of the communication resources. So based on this, people proposed federated learning. The idea is like we still put the data, store the data at different devices. Then we train we train a joint model, and but the communication between the server and those different devices or clients just send some intermediate parameters. In that case, we don't need to send the data to the center or at the same time, and we can those devices can preserve the privacy. One of the idea is we installed a certain we installed a certain camera at different mobile phones. We want to know the features of those different camera, right? One of the idea is that we send a picture to somewhere, and then through this picture we analyze what's a feature or what's the benefit or advantage of those different cameras. The problem is if we send a picture to certain places which may have privacy issue. So using federated learning, we can do that. That's the original idea of the federated learning. But anyway, most important thing is for the federated learning, we need to transmit certain parameters, immediate parameters between server and the different clients, and also we transmit them iteratively, keep on doing that. And therefore, if we do those kind of the transmission, then we have communication distortion. How do we deal with that? And with the distortion, perhaps the performance will turn bad, and so on. So in this talk, I will talk about the impact of those distortions on the convergence of this approach. Okay. This is the original federated learning issue. The basic idea is that we have a fusion center who get the locally updated parameters from different clients. Then we then this server, the central server, will do the parameter aggregation, and this is called a centralized one because we have a fusion center. On the other hand, we can have a decentralized one. The critical idea is that rather than send something to one center, and each devices can listen the send out the information from the other users, then it can do the aggregation itself, because we are talking about the wireless communication system, and the wireless system itself is with the property of the broadcasting. So we can each one can do aggregation itself rather than we have a centralized one. And of course, each one has a disadvantage and advantage. But anyway, and they both have some critical issues. For example, how about if we have communication distortions? How about if we have the attacks and the privacy computation, specular effect, and so on? And in subsequent talk, I will talk about some approach which can partially address those issues. And actually, we talk about centralized one and decentralized one. They mathematically they can be expressed in this format. It can be proved as long as those areas E are connected, and they both convergent to the same model, same parameters. And for the centralized one, we want to minimize those cost function, which can be expressed as this format. For the decentralized one, it is this one. Mathematically, their expressions are different, but they are equivalent. And here, each cost function or loss function is determined by the data from each user. Okay, so that's a way. This D1, D2, or DM are the data from the different clients, and based on the data, the clients will generate those kind of the loss function, and this is Fi. It's actually the function of the W. W is the parameter of the model, and of course this one has something to do with the data set. And for different sets, we have a different function, and that's kind of the thing we are talking about. So this is basically the mathematical model, and so we'll talk about the centralized one first. And well, there are many ways there are many works already to deal with this issue. And in this first work, we are mainly talk about our one of the algorithm, which is called Federated GIA, FED GIA. Basically, and we are trying to develop an algorithm which is communication and computation efficient, and we have the more privacy, and more importantly, with a mild assumption, we can ensure better convergence. Here, ensure means not through the computer simulation, we are able to prove, analytically prove its convergence. That's for today's convergence. They are all like mathematically proved convergence under certain condition, not just using computer simulation. You found, well, this one will converge. It's not like that. Well, so this is what we are trying to figure out, and this is the original one we call the Federated. This is our new one, and through the following, we're trying to deal with, for example, stateless issue. And if some user has a bad channel condition, then we may just without using its data and using others to do that. And also we have the computational efficiency, because we use ADMM rather than gradient everywhere. And it's communication efficiency, that is to say, for each iteration, we're not asking all the users, all the clients to send the update to the center. We just maybe partial of them send the data. which is enough, which will not affect the convergence too much. And this is a kind of the, and more importantly, we found that the convergence is pretty quick. This is the basic idea. So we divided the users. For each time, we divided the users into two sets. One is a kind of the, we call it perhaps the channel. You can say, well, one set of the users with a good channel condition, we can communicate. We can do active update. For another set of users, and we don't do the update for all the iterations. And for the first group of the data users, we do update using exact ADMM, which is a pretty no complexity compared with the gradient approach. And for the other set of users, we use the gradient approach, but we only do one iteration because we set their knockout parameters are all the same. For the another one, for this, we keep on doing updating using exact ADMM. But after K0 step, at here, we do global aggregation using all the users. Then we divided them again into two sets, and then we do this iteratively. Then we found that this approach is communication efficiency, computational efficiency, and all with more privacy and more realistic to implement. Let's talk about the convergence. I'm not going to, yeah. Yeah, that's right. Yeah, you also broadcast. Yeah. Not only, whatever you hear. Yeah. I will give an example. You will know, maybe know better. Yeah. Okay. That's a good question. Okay. Okay. So this is the first the convergence for the first approach, and our assumption is the for the gradient for every function is Lipschitz continuous with, and also we assume it's never set bounded. Of course, those conditions are pretty easy to be satisfied for almost for lots of applications. And under this condition, we can prove their convergence. And we talk about the convergence of the gradient. And we also talk about the convergence of the cost function. And those are results. And for the gradient, and we can prove it will be like with the speed of K0 over K. K0 is we have every K0 step to do global aggregation, and K is the total number of iterations. And for those cost function, this is the optimum one. This is the convergence of the at the case iteration. We can prove if they satisfy certain like a KL condition, which is Kaldica Noyajewski property, then we can prove its convergence with this speed. If on a strong convexity, and for example, it's convergence like this. This is a linear rate. Anyway, this is some concept in convergence, and we can see their performance, and there are several other methods, and this is our method that we can see for the type 1 convergence, and we require epsilon is a small number, so one over epsilon is bigger, and so those convergence need 1 over epsilon number of iterations, but for some of them need 1 over epsilon square. which is basically a bigger number. For example, if epsilon is 0.05 and 1 over epsilon will be 20, and while 1 epsilon square will be 400. So this method is basically compared with some of the other existing methods. It's convergent quickly, and also for the type 2 convergence, we have the same situation. I'm not going to talk too much about it. The others are with 1 epsilon, and but for this approach, which is require much fewer iteration to converge. And this is the practical convergence curve. And as from here, we can see the quick convergence of our method. Of course, here I just ignore the mathematical derivation. I think if you are interested in this work, you can look at our paper, which I think I listed the references at the end of this talk. And so this is a work you can see, which is published in a couple of years ago in signal processing, and we can improve that method actually. And this is a more or comparing. For example, here we're talking about the communication around. We are talking about the time. Time, which means execution time of the program, which is of course directly related to the computational complexity, right? So from here we can see the new method require fewer communication around also, and it require short time. And so this is communication efficiency. This is also computational efficiency, and so on. Well, this is the first approach, and let's talk about another approach, and which is more or less similar to the previous one, but we do even like more extreme. We divided the users into 2 sets. The users in a selected set, we say we do aggregate, we do exact ADMM. For the other users, we don't do anything. Well, we just do those reselection users for K0 times. Of course, it's we are doing these things iteratively for every integer number of K0 step. We do reselection of the users, and so that each user have, if theoretically speaking, infinite number of chances to join the aggregation. You cannot say, well, we fix this C1 for all the iteration, then you just ignore the rest. So this doesn't work. You have to keep on selecting so that every user have a chance to be chosen with certain probability. Right? As long as this is satisfied, and we can do this kind of the work, and we can prove its convergence. And as compared with the other approach, and for the other users, we do the gradient approach, and but we only do once every K0 step. And anyway, and this is for more regarding this approach, you can see our paper published in PAMI, and basically this is basically the similarity and the difference between those 2 approaches. Similarity, we do aggregation at a certain iterations, and we use ADMM. This is a similarity to update the subset of users. The difference is that we don't use we do not do a standard stochastic gradient approach for the other for users in other sets, and we only solve the problem through inexact ADMM clients, right? And this is for the convergence, and that convergence are similar, and but because we do them in different way, we still need to prove it. and this is the convergence of our approach. And again, it's O 1 over epsilon, and epsilon is the error tolerant, and we can see this is the required communication round for our approach. And this is more about the communication round. This is the time, and in both cases for our approach, and with communication efficiency and of course computational efficiency. And perhaps you realize the one thing here, right? For this approach, we only do exact ADMM, right? To optimize. You don't do gradient, right? Originally, you do the gradient for the other users. Here, you don't do the gradient at all. And the question you may ask, can we do this in general using exact ADMM rather than use the gradient? The answer is yes. At the end of this talk, we will talk about this approach, a general approach about that. This is also our recent work published. Anyway, let's switch to other topic, which is the decentralized federated learning, and to answer the question by Professor Wen. So again, this is the previous one assumed, centralized one. Here we skip the central or fusion center. Everybody can be a fusion center, because the communication is something like a broadcasting. Like when you broadcast your information, everybody can in the loop can hear. If they hear the information, they can use the information to update. So this is the way. And then let's talk about this approach. Okay. So this is one of the first approach we figured out. And then the basic idea is that, well, each user, for example, device 1, in step 1, we do local stochastic gradient update. Rather than after that, we send it local information. Originally, you have to send to the something called a fusion center, or that to do that. And but here we just broadcast it. In that case, other users can hear it, and after other users hear it, and of course, the other user can also broadcast their local information, and the device 1 can hear. And once the device 1 hear it, then we can use those information from device 2, device 3 together with its own information to do aggregation to get a model. So everybody can be a center, right? So the question you may ask, how about because we have broadcasting, we do the communication, right? And for example, if at the first time slot, and the channel between device 2 and device 1 is not good, in this case, we cannot get the correct information from device 2. What do? There are 2 ways to do that. You can ask to retransmission. That's a communication problem, right? Until you get correct information, right? Another way is if we find the received information is incorrect, we just ignore it. We use user 1's local information instead, right? We cannot find the correct one from device 2 because due to the communication distortion. Then what we need to do, we just use the local information as if it's the information from device 2 to do that. So we do this. Not from myself. No, I cannot. Local is not. Why should I use local information from others? How about if others are also incorrect? I can guarantee with 100% of my own information, we can get it. I can get it. Yeah, but you need to do aggregation here. You need to the information device from device 2, device 3. Also, you need the information from device 1, right? And here I just ignore it. And but here you just use your own information substitute. That is to say, you use your own local information twice, actually. And for the others, the same thing. And for example, if in the first time slot, and you know, for example, the here you cannot get the information from device 1. You just use the tools local information to do that, right? And the question here is there are two ways. I think the first way is you keep on do retransmission. You are increasing the communication around. But when you do the iteration, you can guarantee all the information we use is accurate, right? And it will convergence quickly. But the communication, you need more communication around. On the other hand, if you use your local information instead, you are using inaccurate information. For each iteration, you only need one communication around, right? You're not asking for transmission. Because you use the inaccurate information, the system will converge slower than the way you use accurate information, right? The question is which one need fewer communication around, and this is the question we are interested in. But anyway, the convergence of the previous approach, I mean, using inaccurate information, we can prove it has something to do with several parameters. One is the number of the device number. Of course, its convergence speed is in proportional of the square root of the number of the devices and also the number of iterations. And of course, it's the larger the number of the iterations, it converges quickly. Yeah, this is the error. Okay. We are just talking about a type 1 convergence here. Yes, it's the convergence of the gradient. Okay. But anyway, this is a theoretical proof, and also we proved another issue. Here, I'm not talking too much about it here. And we found that using inaccurate channel information under certain condition, we get the same convergent rate asymptotically. Here is it asymptotically? It's still slower, a little bit slower than using accurate information. But asymptotically, they are almost the same. And if you're asking another question, which one require fewer communication around, using unreliable information require fewer communication around, even though it's convergent slowly, but not that slow, right? And but on the other hand, if you use accurate channel information, even though it converges quickly, but you need to keep on asking retransmission, it still need much more communication around. Well, that's it. And this is a simulation on those kind of the performances, and as we can see, this is the accuracy, and it is much better than the other approach, and so that's this one. Another one is we call a sparse DF decentralized decentralized federated learning. The idea is like this. This is a more general one, and we did it recently. And here we are talking about something like a sparse one. We found that the gradients are sparse. That is to say, most of the gradients are almost zero, and some of them are non-zero. And in that case, we can use we can exploit the comprehensive sensing to improve the communication efficiency. I'm not talking about, this is a literature review. I'm not talking too much about it. Our work was published in TSP, and we also consider to make the system more privacy. So we use something called a different privacy, and here we just assume we can recover the gradient using one bit information. Anyway, this is a approach we are talking about, and here we use several things, and we only transmit certain information. We do the compression, and only transmit significant information. Also, on top of that, we are using the a differential privacy to make the system more more privacy. Of course, whenever you use differential privacy here, it's like you added some noise to the some kind of the parameter or gradient, which will affect the system. But you are improve the privacy. This is a basic method, and this is the way we are doing compression, and for this approach, and we proved it's convergent like that. Okay, of course, this is the type 1 convergence. We're talking about the convergence of the gradient, and from here we can see it has something to do with 4 parameters. Here are 3 parameters, 4, and here C1 it has something to do with the approach, and T the number of iterations. Here, in addition to this, we have another 2, and this epsilon is the average power of the partial of the different privacy. This eta have something to do with noise gradient, noise variance eta here. So this is basically what we have proved, and for this approach, and basically this approach has more privacy, and also it's more communication efficiency because we're using just 1 bit compressed sensing to do that. But anyway, this is the performance and of the communication around, and from here we can see we need a much fewer data transmission, which means its communication efficiency, and compared with the other approach. And this is we talk about the convergence. It's also convergent pretty quickly. This is our approach. Okay. So this is another convergence, and so far we talked about too much convergence, right? And so the last one we talk about our recent work, something called extended federated learning framework, and basically, as we can see from here, we don't need the gradient to search for to optimize the system. We can use the exact ADMM instead. So under certain condition, for the federated learning, and we can using this method. This is a pretty fundamental one. So this is the last one we are talking about. So, and this is the background. I'm not talking too much about it. And our basic idea comes from here. This is we have already mentioned this, and this is a kind of the things we are talking about. The model is the same as what we have before, and I assume we have M data set. Each could be regarded as a data set in different devices, and also the loss function is like this. Basically, the mathematical background is the same as the previous one, and I'm not talk too much about that. And this is a basic approach, and basically, this is for all of them, for perhaps user 1. This is user 2. This is user M, right? There could those M users could be data set. They could be put at the same location, but they are just different data set. Could be at different locations. In that case, at this place, you need to do like transmission for the aggregation. Either way is fine. The critical idea is here in this kind of the one big iteration, you divided the data set. Originally, you have a data set one, right? You divided the data set one into n disjoint data set. So those data set D11, D12, D1n are disjoint. And also D11, we put them together, they form original data set one. So you divided the data set disjointly, right? So that's the idea. For all the other data, we do the same thing. And for each small iteration here, and we use inexact ADMM to do the optimization. And then we can prove this approach can substitute a commonly used gradient approach, and will have much fewer, much less computational complexity. For this one, we have already proved, and this is the thing here. This is a comparison between our approach and the gradient approach, and in terms of the convergence and so on. Also, this approach convergence under very not that complicated situation. So this is our approach, and we can see for different one we can see the performance, the accuracy compared with the other approach, and which require gradient approach. I guess this is a more simulation, and this is the performance. This is performance, and yeah, we can see it. So this approach can be generally used to the federated learning, and it may be potentially extended to the other system. But that one we didn't try. We don't know. And so this one tells us for the federated learning, you don't need. It's not necessary to use the gradient approach. We can use the ADM inexact ADM instead, which is with less computational complexity. Right. That's I think that's all for my talk, and this is more comparison with the nodes, and yeah, we can see this approach. Yeah, it's convergent quickly. Well, in exact ADMM, and the way we divided the whole data set into different subsets. Yeah. So the other approach, we compare with a similar situation. Yeah. Well, I think for almost all of our method, you can find the program on the website. And if you cannot find it, just send me email. You can run the program. You can see what happens, right? The publication, they are all here, right? You can find on the website, either archived or on the journal. That's all of my talk. Yeah. Any question? Is there any restriction for the complex optimization problem or any kind of problem? I know that the discourse with the operating complex. Uh, the problem is I think Professor Wen's problem is we're talking about the convergence. The problem is where to converge, whether it's a global minimum or local minimum. Yeah, for that one we cannot control because it depends on the initial condition, which is the same as the gradient approach. It converges to some point and similar to the gradient approach, right? You cannot control it or guarantee to converge to the global minimum, but we can guarantee we converge to some minimum, which could be global, could be local. I believe most of the cases it's local. Yeah, but it doesn't matter if it's already very good. And I think this is a general problem for all the neural network issue. You cannot guarantee to converge it to a global global optimum, whatever. Yeah. Yeah.
The problems involve the constraints without the convergence
Can be what?
guarantee.
Yes. All even though I didn't prove those kind of equations, they're all analytically proved, not through simulation. So whenever we say convergence, yeah, it can be guaranteed.
The problem involves constraints because I think problem does not contain constraints.
That's a good question. I believe it's more or less similar, but we didn't try. Yeah. Perhaps you change something. Yeah.
As long as there's some the assumption that compiles is the constant gradient compiles this is the assumption.
Yeah.
But the assumption always can be clearly guaranteed in the critical situation.
Yes. Because if you want to prove something is convergence analytically, you need some condition, right? Those are conditions, and if you analyze is good, and which means you use less condition. And for most of our convergence analysis, we need a fewer condition or assumption with other approach. And I believe most of the approach can be satisfied in our analysis. Yeah.
So that if you think about lots of the local sensors, maybe they if they can compare and they different environments, maybe the gradient, the area of gradient is at a lot different. So I just have to they can converge.
Yeah. Yeah. I think our problem we didn't consider the constraint, but I think the more or less all the constraint problem can be equivalent to the problem without constraint. Yeah, you just can't just restrict it to, I mean, parameter sets. Where to choose parameter, something like that. Yeah, which may need some kind of the quick fix to do that. It's not obviously in certain situations.
I think about problem with general
Yeah. In most of the cases, some of the cases maybe you need some tweaks. Yeah. Yeah.
So I'm not sure if you can
I'm not sure either.
learning. Can you explain in detail a bit?
I don't know. I don't know GPT too much.
Another question is, okay, this one, how can artificial intelligence be used to jointly optimize energy harvesting, user access, and resource allocation?
Okay, this energy harvesting problem. Again, I didn't do anything on energy harvesting, so I cannot answer this question.
Yeah.
Oh, this is a previous question, I think.
Yeah, that's all.
Oh, okay, thank you.
Thank you. So, yeah, thank you everyone for joining today talks. Tomorrow again we will start at 9 a.m. and we will have 3 more talks and one lab tour. That one will be live demonstration of active RAS at MIMO Communications. So see you tomorrow. Thank you.